You know, how before a flight they always say, we are actually going to Alaska. If you're not going to Alaska, please, make sure to get off. I actually saw someone sort of say, ah, and get up and run out of the flight once. That was pretty. Okay. You're going to 122 as well. Okay, sorry. All right. This is 162. This is, I think they said, what did you say? 106 Stanley. Okay. Anybody else? Sorry, we had a bit of a change, and I'll tell you why we had a change. Well, there's several reasons, but there's one of them is good for you guys. So, welcome to 162. Sorry about the little mess up here. I've never taught in this room and didn't realize I needed a key. All the other rooms I teach in, I've never needed a key to get access. So, can everybody see? Yep. Looks good. Can you hear me? All right. So let's start by who am I? Okay. I am John Kubitowicz. Most people call me Kubi because they can't pronounce my last name. That's fine. I've actually done a lot of different things which give me sort of a unique perspective in this class, which I hope you guys will enjoy. I've done hardware design. I actually designed a complete multiprocessor at MIT called Alewife. And there's a little picture of one of the chips that I designed there, the CMMU. I've done a lot of operating systems work. Worked for Project Athena, also at MIT, which, believe it or not, was one of the first projects back in the day to actually have people's home directories on a distributed file system, so you could log in on any workstation. How's that for strange? You guys take that for granted now. Been a bit of an OS developer, worked on high availability systems, and recently I am now the lead OS researcher for the PAR Lab, which is a new parallel lab that just started here at Berkeley. And you'll be hearing a lot about that as the term progresses and so on. But the high-level bit there is that we're looking at how does the world change with multi-core processors. And actually, the term that we really use is many-core because we're looking at 64, 128, 256, so on. I also did a lot of work in peer-to-peer research. The Ocean Store project was something that I was pretty well known for. Few years ago, and we were kind of looking at storing data very widely throughout the internet and basically making it look as if it were local as far as speed were concerned, but would last forever. Come on, you can come on in if you like, or not. And the other thing that I do is I actually do research in quantum computing. Now, this is a little bit off topic, but at the end of the class, I always do a lecture on anything that people want me to talk about, and they've actually convinced me, even in this class, to talk about quantum computing. It's been done. So keep that in mind. So what are our goals for today? We're going to start out by asking a little bit about what is an operating system and what isn't it. And we'll give you some examples. And maybe we'll end up with a question about why we might actually want to study in operating systems. And we'll say a few things about how the class works, there are tests and labs and all that kind of stuff. But fortunately, you don't get to worry about that in the first week. We start worrying about it next week. So. Okay. And normally you won't see me running around trying to figure out how to get the display working and so on. Hopefully we've taken care of that problem. But the way I run this class is very interactive. If any of you have ever taken a class with me, has anybody taken a class with me before? I think we've rolled over. I used to teach 152, and I had a period of time where my 152 and 162 folks kind of overlapped, but I don't think that happens anymore. But anyway, the point I was going to make is I encourage people to ask questions. So please do. More questions, the better. Okay, and if it turns out that questions are going too long on, I don't know what the last digit of pi is or something, I may stop, but only after we sort of got a lot of discussion going forward. So, all right. So, are there any questions? Anybody curious about any of these things before we actually start, or should I just go forward? Okay. These are, by the way, good fodder for final lecture topics if there are things that you guys want me to talk about. So, okay. So you've probably seen many times slides of this form. How many people have seen a Moore's Law slide before? Okay, good. You've probably heard many things about Moore's Law. You've probably heard, for instance, what it is. What is Moore's Law? Say again? Computer power doubles every 18 months. No. No. But hold that thought for a moment. And this, by the way, it's an okay thing to have said because people commonly call that Moore's Law. That's wrong. That's called Joy's Law, but that's okay. What was it? Number of transistors doubling on some short time span. Okay? And what you see here is a log linear scale. You tend to see a lot of them in computer EECS these days. And what it means here is that basically, as time goes on, we've got a doubling factor in the number of transistors. Okay? And sometimes people show just the raw number of transistors. These are actual chips. But the fact that they fit a line on a log linear scale is kind of an amazing thing. That's an exponential curve. It means things are doubling on a regular rate every year or year and a half. Pretty impressive, okay? Now, what is kind of funny here, you may not know the story of Moore's Law. This is Gordon Moore, by the way. He was asked at a conference way back in the years of the 4004, which had so few transistors that the way that they made the masks for the 4004 was they laid out a huge piece of plastic and they drew little transistors on them, and then they photo shrunk it down so they could make an actual chip out of it. He was asked, how do you see the number of transistors on a chip increasing or decreasing over time? Remember, increasing, hopefully. And what he did was he plotted a few points on a log linear scale and said, oh, obviously, it's going to look like this, for decades. And, of course, nobody realized that what he said was true. This is what actually happened. Now, the reason I bring up Moore's Law is that this greatly impacts pretty much anything you're going to take in computer science, but it certainly impacts operating systems because this translates directly into complexity. More transistors, more complicated. It also goes directly into power. Okay, and power in several forms. One in raw power, I'll mention that in a moment, but also in what you can do. Okay, so it's kind of an exciting backdrop. Here, for instance, is something you may have never seen it laid out this way. Dave Culler does this now and then. We do this occasionally. But this is kind of the spectrum from little tiny MEMS devices that are being done in the building here to this is a little silicon ant that can walk on 4 legs on up to sort of a huge global scale server system and everything in between. And why is this? This is because of Moore's Law. Okay? And the way that this is appropriate for this class is this is a huge parallel system. All right? And many different individual operating systems somehow all work together. And when you're done, the system mostly works. Okay? The number of servers involved in making just this simple cell phone work is pretty amazing. Okay? You got the towers that I pass by. You got the servers backing the towers. You've got mail servers that this thing queries on a regular basis. Yada, yada, yada. You go on. Many. Okay? So anyway, so that's why this class is particularly interesting, because the question is, how do you build the management software on top of these things so that something actually works rather than is a chaotic mess? Speaking of which, so this is similar to a car that I purchased recently and ran into a problem. I turned it on one day and several lights on the dashboard were on, and they're claiming that sort of massive failure in braking system and so on. Now, it turned out the brake still works, so I could drive it to get it fixed. And what did they do? They rebooted it a couple of times. And then the third time I went in, they said, okay, that's not working. Let's replace a processor. So they completely replaced the processor. And that didn't work. Next time, they replaced a different processor and 4 sensors. Okay, so this brand new car already has 2 new processors and 4 new sensors. It seems to be working now. But that tells you kind of the level of complexity that we're at today. Not a car anymore. This is a computer system. Okay, I'm waiting for the Control-Alt-Delete on the dashboard or something. That would have been useful because I wouldn't have had to take it in so many times, you know? So Here's another interesting graph. This is David Culler's